Welcome back to the Algebra 2 series. Today we're looking at one particular example from our textbook which asks us to find a minimum volume. And as you see from the figure, I have a picture of a right circular cone that is circumscribing a sphere, and in this case that inscribed sphere I'm drawing in 2 dimensions, but is actually a 3-dimensional picture. You'll just have to imagine this. Creates a couple of things for us. First of all, it creates, as you can see from the figure, two similar triangles. And the way we show that they're similar is because the top angle right here is common to both of those right triangles. Let me put in a couple more variables here. Notice that the radius of the sphere extends all the way around, and therefore we could determine that this length here, which is the hypotenuse of that smaller triangle, would be little h minus capital R. And we're going to use that a little bit later. So that's an important dimension to use. And I guess that's the only one we need to denote right now. Notice that the R is at the bottom. So there are a couple things we want to do. First of all, notice that it says that the radius is R. Of course, in the end, it's not going to matter what the radius is because we're talking about a somewhat of a proportion as we fix that radius. But the second part of it is that we're trying to write a volume formula in terms of theta. So let me erase that for just a moment. I want to write a volume formula or a volume function in terms of theta. And of course, that theta should not have any other that function should not have any other variables besides theta. Of course, it could have an r in it because r is not a variable. It's instead just a constant that will show up inside of that function. So that's going to be our goal. Before I do that, though, I want to establish a couple of relationships. And let's start with writing out the volume of a right circular cone, which is 1/3 pi r squared h, where r and h are the 2 dimensions of the cone. The base radius is r. The height is here. That's the vertical height. Those are the 2 variables we're going to try to replace. So what I would like to do in one of my initial goals is to try to write r and h in terms of capital R and theta, theta being that base angle. So let's give this a try. 2 of the relationships we want to look at then are trig functions. Let's look at the first one. That's the tangent of theta. And this is the theta right down here. We're going to start with the first one. And notice, of course, the tangent of theta being here, opposite over adjacent is going to be little h over little r. Tangent of theta is equal to h over r, opposite over adjacent. That one's a simple one. The one that's a little trickier is the fact that since these are similar triangles, we actually have another theta right over here, this little angle. And notice that this r and the h minus r are located in the adjacent and hypotenuse positions. So I would write as my second relationship the cosine of theta is, of course, capital R, the adjacent over the hypotenuse h minus r. So we've got those 2. And notice here that we can do some substituting. So I'm going to do these right away. The first one I'm going to notice is that if I switch the first one, I could rewrite this as r equals, excuse me, that's not an n, let me redo that, r equals h over tangent theta. So that's important. And then, and we'll see more of that later. So I'm just going to stop right there. See, we've got this going on. And then on the other equation, I'm going to start working with this one. I'm going to need to scroll this down a little bit, but that's all right. Let's work with this one. Let's multiply across, first of all. That's going to be the cosine of theta multiplied by h minus r, and that's capital R, or h cosine theta minus r cosine theta is equal to capital R. This is linear, so I can solve for h. H cosine theta is equal to r plus r cosine theta, and therefore h is equal to r plus r cosine theta over cosine theta. I'm not even going to reduce that right now. I'm going to leave that just the way it is. That looks great. Now moving this one down a little bit, I'm going to do a couple more little things here. R is equal to, since it's h over tangent, that's the same as h times cotangent theta. And since cotangent is cosine over sine, what I'm going to do is I'm going to replace the h with this expression that I just found a minute ago. So that's going to be r plus r cosine theta all over cosine theta times cotangent, which is cosine theta over sine theta by definition, and now we see we have a nice cancellation here. So we find in the end that the radius of the base radius of the cone is capital R plus r cosine theta, and that's all over sine theta. Well, here we've got our two substitutions. They look very much alike, and they're actually too close together, I noticed. But anyway, we see that we can replace the r here, and we can replace the h here. So we end up with the following. And I want to just point out that r plus r cosine theta they both have the same numerator. And since we are squaring the r, h is to the first power, that means that our numerator is going to eventually be cubed. So if it's all right, I'll just go ahead and write the entire function out. So repeating what I have above, 1/3 pi r squared h. This time we're going to replace everything and write it in terms of theta. Of course, capital R being a constant. The excuse me, the capital, the small r, the base radius is going to have a sine squared theta, because I'm squaring this one as pi r squared, and then that's going to be r plus r cosine theta, and that guy is squared. And of course the h, which has another one here, r plus r cosine theta, and this one is over cosine theta. That looks like a very cumbersome uh, function, and I'd like to simplify it just a little bit. First of all, I notice that I have in the numerator an r that can be factored out of this term, and of course an r squared that can be factored out of the other term. And that would give me r cubed 1 plus cosine theta cubed. Should have done that long ago. And then the denominator, and so what I'm trying to illustrate here is that I've got 1 plus cosine thetas multiplied together, and the r cubed can come out front. And the reason I notice that is because I've got a sine squared right over here. And we know that sine squared, I'll just do this as a little side work here, sine squared theta can be written as 1 minus cosine squared theta by the Pythagorean identity, which can be then factored as a difference of squares. 1 minus cosine theta, 1 plus cosine theta. And lo and behold, I see I can then cancel one of them with the numerator. So I'll leave this to you if you want to do this in longhand, but I notice what's left over then in my denominator. Instead of a sine squared theta, I'm going to just have the 1 minus cosine theta, and I'll cancel one of the 1 plus cosine thetas in the numerator. So writing this out as a very large fraction, I've still got the pi in the numerator, I've got a capital R in the numerator, I've got a 1 plus cosine theta quantity squared in the numerator. The denominator, which used to have a sine squared, no longer has that, but it still has the 3. It has instead a 1 minus cosine theta, and it has this remaining cosine theta that we missed. Well, we didn't miss him. We just didn't have anything to do with him. So there you go. Nothing else cancels. And, oh, I did make a slight error here. I believe this is r cubed. There we go. That's better. Okay, so that is the nasty looking function that is the volume of the cone in terms of the base angle theta. So that was a lot of algebra within the trigonometry. Now, of course, this is not an easy one to graph. It would be very difficult to graph this by hand, but we can use a graphing calculator. We're going to need to replace the r, though. So just in the context of the example, let's just write, for example, um, let we're going to let r equal 2 centimeters or whatever units. Doesn't matter. I'm going to make that 2 units. And then that way we'll end up having a nice clean number to put in there, r cubed being 8. So we'll substitute r cubed equals 8. So we'll actually get some volumes to look at. So that is our job. Let's see if we can minimize that. So the question, of course, let's go back to the beginning. It says, find the base angle theta. So that's what we're looking for, the theta, that will minimize the volume of the cone. And of course, that's our goal here. So I'm going to jump away from the presentation for just a minute and go over to our graphing calculator. And I managed to put this function on the graphing calculator. Notice that it says 8 pi. Here's the 8 pi. And then 1 plus cosine x quantity squared over the 3. You see the 3 in the denominator, the 1 minus cosine x, and the cosine x. So we'll graph this. And we're graphing this in degrees. So I've managed to work this out so that my mode is in degrees rather than in radians. And that way we can see our answer as an acute angle, theta. And there we go. It looks like it comes down, and then the minimum value should be somewhere, it looks around 70 something degrees. Let's calculate that. So second, we're going to calculate a minimum, which is number 3. And as you recall, doing this on the graphing calculator, we want to move our value here for the left bound and then move it to the other side. I'm just pressing the right arrow key so that I can get that in the right position over here somewhere. And then go ahead, press the enter again. And then it asks us, would you like me to guess? And of course we do. So what it is bringing us, and if you notice right here, it's giving us a nice x value, 70.528. So going back over to our other problem, we've already filled in our values here. This was pi r cubed, 1 plus cosine theta, all squared. That over 3, 1 minus cosine theta, and then a final cosine theta back over here. And the answer that it gives us is about 70.5 degrees. That's an interesting answer because it's not a known value like 60, something that you would think, okay, in an equilateral triangle, it might work best. It's nothing like 75, one of our pi over 12s. It's a very unique answer. And hopefully that gives you an idea of how we can handle something as complicated as number 54.